I got your mail at the last moment. So you said the website was.
Yeah, I couldn't get we have to load it all.
Yeah. Was it the same? So everyone had the same problem, I suppose?
Yeah, so it's. I just submitted my quantum exam a few minutes ago.
Oh, so it.
Like, I submitted it like 15, 20 minutes ago.
Okay.
I wasn't able to
So
submit.
there seems to be a problem in the.
I wasn't able to submit my homework, if that's what you're asking.
You could, Avinash. What's the magic you use?
What?
You could or you could not.
What was that?
You said you could upload something on
Yes.
for the quantum 15 minutes back.
Yes.
Okay. So it's not permanently down there. And there's sometimes it is down, sometimes it's not. Jordan, were you saying something? Hey.
Yeah, I can try again since I'm at home, but I also couldn't get it to work. I'm not sure. It just kept every time I tried to submit, it just kept saying error.
But now it might be closed, right? If it is extra credit. Extra credit, I think I don't allow. I didn't bring my file in the hurry. So
Now I can stay here.
now you can stay here, Alia. Hello, Alia.
Hello.
How was your qualifiers, Rob and Ali?
I think it's good.
You didn't take the quantum, or did you take it? No, you didn't. That was that I was personally unprepared for. The E&M, classical mechanics, okay, quantum. I've been working at like Stairway Moses level, and this was second half of Griffith level.
So how does this work? Like, do you have to?
This is my free attempt.
Oh.
Yeah, I could have written limericks on it. It doesn't matter. I just wanted to see where I stood since the last graduate class I took in physics was 97 before this.
No, what I was asking was like, let's say you have classical mechanics, you have E&M, and you have quantum mechanics. Do you have to pass all of those
Yes.
at the same time?
And then so when I do the next one, I can decide to switch one.
Is it like one day it is classical mechanics, the other day it is E&M, that way?
So Friday, Saturday, and Sunday.
Well, if there's any insight to the quantum part, I'm guessing Dr. Bird does that portion. And when I took his course in quantum, it was quite a bit different than previous quantum courses that I had. So if it leans towards the way that he does things, I could see how, unless you've had a course with him, which I don't know that you have yet, it could be pretty difficult, I'm assuming. Because he does things a little bit differently and asks questions slightly differently. And
the questions were fairly straightforward. I mean, he did a good job of asking questions that were somewhat straightforward. It was the dealing with notation and stuff like that I haven't done for a while, and
I'll say his course is like a building block. Like if you don't follow the way that he does things from the onset, it can be difficult to answer his questions. I think that's what I'm saying.
Okay, Jordan, what book does he use?
He uses Ballantine, a book by Ballantine, but he references pretty much every quantum book that you can think of.
Yeah.
And he doesn't necessarily follow Ballantine to a T. And I'll say this, but he likes a lot of things that are in the Ballantine book, but the Ballantine book, see, the issue that I had in his course was that when you start the course, you basically start in like chapter 8 or 9 in the book, and they have a very specific, in that book, it's, if you don't start from chapter 1 and follow their notations, it's not like picking up a Griffiths book or you know, something along those lines where you pick it up, and if you don't understand something, you just like flip to chapter 2, and then chapter 2 gives you notations or something, you know, and then you can follow it after that. The book isn't quite like that. It's you really have to start from chapter 1 and then chapter 2, and it's a big book, so you have to put in a lot of time and effort, and that's why I struggled, because I have a little bit less time, I think, than some people, and I was trying to just get through the chapter after chapter after chapter. And then when we switched to online last semester, it made it difficult because he kind of switched away from Ballantine and just went all QNet. So the best way to do his course, I think, is, because it's all of his thoughts regurgitated onto a platform, so go to QNet, review all of the things that you should know. Basically, he gives like matrices, and you may think you know all that sort of stuff, but I think if you really put in the time and effort to understand the introduction to QNet, then go chapter by chapter through QNet. And the first semester course doesn't even really get into the part 2 of QNet. I think that's more of like second semester, but QNet is like your key to his courses, and I think the way that he thinks. Use that. If you haven't been to it, I think it's QUENET. QNet.
Good. Good. Okay.
Yeah, it's QUNET.
QUNET.
Yeah, good. Moses, we were just asking about you.
Yeah, I was in St. Louis this weekend, and my intention was to get up this morning and come back to Carbondale, and I didn't. So I'm still in St. Louis.
Advantages of
Yes, definitely. Mm-hmm.
you're the few. Yeah, I did grade the midterm exams. Last one I got it only during the on Friday or something, but it was graded for most of you before. But then I promised that I will add 10% to what you lost. So that should all be updated at this point. So this is a right time to check your grades, like by any chance if you are worried where you stand. And this is also a good point to assess yourself. Whatever your grade is, often I've noticed that this is the grade that might, if you keep working hard like this or keep doing whatever you're doing, this is probably the grade you will have at the end of the semester. So that's for your information. I was supposed to bring the file, but I think I have the grades. I don't remember the numbers before the curve, so this is after curve. Highest is 100 total full points, and then you have a couple of 92s, and then there's a couple of 90s, and there is the 80. Okay. Yeah, I think that's the, there's one, so there's one more 92, I think. Either there's one more 92 or there's one more 90. So that's the distribution, I suppose. So that's 7 grades in there. And if you have any concerns about you're not satisfied or anything, this is the time to meet with me, ask me anything. Most of you have been doing what you should be doing. And you should all know what is going on. So it's going to be repetition sort of this 3 times in a sense, including the final exam. I think it's not very different from the usual midterms. So there should be no surprises from this point. Okay. Maybe I should also say that those are right on the boundary. That I did see that this is not coming very naturally for many of you looking at your homeworks and all that, but that's where the teaching or that's where I am supposed to contribute. So to you guys, most of the times it is you guys trying to practice and get it done. So it's not smooth for I can see for you guys, but try to make it smooth. Hopefully there'll be a lot of vector calculus that will be coming in and gets more easy. Okay. So with that, I did post a homework of 5. This is a very small homework I posted so that we get everything done by, for example, whatever we are doing about continuity equations and conservation laws, we try to finish today, and then we do what is called macroscopic electrodynamics from the next class. What is macroscopic? Oh, by the way, what is macroscopic electrodynamics? So what is macroscopic electrodynamics?
Large scale, like looking at it from.
Yeah, a little more specific.
Looking like at like net polarization or net magnetization of a collection of charges.
Yeah, that's correct. So basically, until now, we have been talking about point charge, things dealing with point charge, dipole, and so on. Macroscopic deals with actual materials. We talk about what will happen if there is a conductor, what will happen if there is a dielectric, what will happen if there is a magnetic material. So write down Maxwell's equation as far as possible for a material medium, and like all the epsilon naughts that we had, that will get upgraded to epsilon, and there are some changes that come. So we'll try to switch over to that on Friday. But meanwhile, there is a small homework due. This is October 2, and this is on Friday. And when I say small, from my perspective, it is small. I did expect the exam to be a lot more easier than what you guys felt from what I could see, how you guys felt about it. So there's a lot of difference in perception between what I think just understandable. But I try to fill in that gap. I can never do it. I always get surprised. Like this semester was, I expected the exam to be significantly more easier than what you guys felt it to be, especially problem 5. I expected, at least when I describe it, it would have been easier, but I think almost everyone struggled, or except for exceptional case. Other than a couple of you guys, almost everyone struggled, which is okay. I don't think struggling in that problem is really a big measure of what you guys, your grades are reflecting. I did not grade that. It was just for attempting, if you noticed. The problem 5 was only for attempting. But problem 1 and 2, those who struggled, even I would say problem 5, right? No, problem 4. I would say, yeah, you should review yourself. So that is what I graded actually, 1, 2, and I think 4. Problem 4 was what I graded eventually. So that's something we should look into. One more thing. So on October 5, right? That's a Monday, I suppose. Next Monday. We won't have classes. No class. And then exam is on the next, so midterm 2. Exam is on October 12, I suppose. Try to catch up for that missing another time. But we did get, on the exam day, we did get an extra class. So hopefully we don't have to, but otherwise we will manage somehow.
So one quick question with
Yes.
the exam grades is how exactly did you're
Oh.
saying grade it then?
So this was total. So whatever total you got, right? This is your grade that you earned in your exam, extra credit and so on. That's your total. Whatever is it? What is it? Assigned points for each. And then what I did was I took 100 minus the total. Oops. If I add this, everyone gets 100, right? But then instead of that, I give you only that much as much you got in extra credit. Right? This is extra credit in out of 1. Right? This is y is less than 1. Less than or equal to 1.
That's the curve on the grade in general, not just I thought you were saying you curved the exam.
No, exam I did not curve at all. This is the whole course gets it. Like more recently, I think maybe until last year or something, I used to curve the exam and not the course itself. So now I like this feature that I give extra credit and which I feel is relatively straightforward daily work. And how much you get in that decides how much you get, how much curve you are entitled for. And there is one feature that I do control, and that is I set A is equal to 0.10. So I was ready to give 10% of whatever you lost, but then it's your score and extra credit that decides how much you can get. But most of you here, I think, got a good percentage. But I remember that as you go forward, the number of extra credit increases, so that probably increases. But and I also noticed that always it's the top students who end up earning the extra credit full. It's kind of doesn't serve the purpose completely, but at least it is more fair, it seems to me. But yeah, again, give me thoughts on that. That's what I have come up with on it. If you guys don't like it, or if you think that extra credit is taking away too much time and management, sometimes there is a course management, right? You spend a lot of deadlines. So let me know. I don't promise that it might change this semester, but it might be helpful for the future students or even the courses that you might take with me in next semester. So do give me feedback on how you find extra credit. Be honest. I don't think I'll mind that at all. It helps because you guys go through it. Many things I don't see it as you would be seeing. Okay. So any other questions on that?
Yes, please. I have a question.
Oh, yes. Yeah.
Does the homework 5 deadline in October 2nd or homework 4?
Homework 4 is already having a deadline of, that was just, homework 4 was supposed to be deadline today, right? I think, yeah, some of you guys took qualifiers, so it was just a, so this is also October 2. Okay.
Yes, because I'm not able to finish the homework 4.
Yeah, so how about this? This is due on Friday, but we will postpone its due date by Monday. Okay, is that so? I'm flexible about that. Reasonable, since there was qualifiers in between. Yeah, so just send me an email and I'll be flexible. But let's try to finish it off. Like let's have a deadline for the homeworks, and let's try to as much as possible finish it off. But yeah, if you have, this can be Monday 3, 4, 5, right? Maybe 5, maybe. But officially it's due on October 2, so approach me if you want an extension. Did I answer your question, Ali?
Yes, I'm talking about myself for homework 4. I finish it, but I'm not able to finish the article. I need time for that. That's it. But But it's okay. I can do it in October 2nd.
No. October. Oh, you mean even by October 2nd you won't be able to?
No. I thought it's a deadline today for homework 4.
No, I think it
It-
is October 2nd. Is that right? Yeah. I think
Ah.
everyone did. I
We
verbally
changed
said
it.
that.
Oh, okay. I think the deadline on D2L is midnight tonight for homework 4.
Oh,
Yeah,
okay.
It is October 2nd.
Yeah.
It is October 2nd?
Yeah.
At some point it changed.
Okay,
Yeah.
got it.
Yeah, I think you guys met with me, and that is the day when I told the Moses that, oh, for you it is different deadline. Maybe that's what you registered. But I did not, D2L, I did not purposely do anything for you, Moses. It's just a uniform thing.
Yeah, I just checked. It was maybe Saturday that I checked or something like that. And on Saturday it was still midnight. Oh, maybe it was October 2nd though, and I just thought it was, I don't know. Anyway, don't worry about it.
Send me an email if there is some problem. Okay, is that fine, Alia?
I don't know, there's no problem.
Yes.
Yeah.
Put it like this, as until now, I have been satisfied with whatever you guys are doing. So if there is a concern about homework, just approach me. I'll be glad to give extension. But at the same time, I don't want to do it, make it so easy that no one stops working. And I've heard from you guys that deadlines help. So let's keep deadlines and at the same time, be a little flexible.
Okay. Thank you. Thank you so much.
Yeah. Okay. Hopefully I can finish. Yeah. So we did do Maxwell's equation as of now, and so this is called Maxwell equations in vacuum. We'll start pointing that out because very soon we will be working in the presence of a material, but we won't work with materials today, but we want to work on Fourier transforms. So these are the Maxwell's equations, del dot E, we write that as epsilon naught. And D equal to 0. Time derivative with a negative sign. Right? I can write this as D, right? It's better. What's J of R, comma P? And you have the understanding that D is equal to epsilon naught E. And B is equal to mu naught times H. Yeah, here's an extra trick. So, I've not taught you this, but looking forward in a week or so. So you have this equation to be right. In the presence of a material, the main idea is that epsilon naught becomes an epsilon, the material property. how does this equation change? So, what is this equation? When epsilon naught gets upgraded to epsilon. So it's just a survey question. I want to know how you guys interpret that. I expect that there might be, naively speaking, that it might be a wrong statement. So just look up your textbooks or whatever you remember from your elementary physics if you have seen this before. Otherwise, just look it up and answer. Okay. That's your equation, and I had suggested that we should try to look this up, write this equation in a Fourier transform space. So most of the time what we will do is, instead of working in time space, it will be convenient to work in frequency space, and same thing with position also. Instead of working in position space, we will work in momentum space or wavelength space. Working in wavelength space is less common. That is usually a mathematical use, but going to frequency space is actually an experimental, like physics happens, and most of your sensors are color dependent. Like when you do optics experiment, most of the sensors in your lab are actually color dependent. So that is, color has to do with frequency. So we get our data in a frequency space. So that's almost a need there, that you have to work in frequency space. But most of our intuition is in time. We are used to intuitions associated with time, and the biggest intuition we have is the intuition of causality. Right? We don't expect the future to come and affect our present, but we do expect our past to come and affect our present. And then the immediate question comes, how does this intuition switch over to frequency space? What is causality? So that will be our main concern in the next 2-3 weeks, if you want. So that's what we are sort of building up to here. So all that involves Fourier transformation. Fourier transformation that we talked about last time. And we said, instead of working in position space, we can go to a Fourier transform of position and time space. We can go to Q. Okay. So these are the three. K is the Fourier transform variables. That's your 3 Fourier transforms related to X, Y, and Z. And that is time, which gets Fourier transform to frequency. Right. Plus infinity. These are your Fourier eigenfunctions. I, K with R minus I omega T. So that's your Fourier transformed electric field. Notice, since exponential of all these eigenfunctions, if you want, I k dotted with R, is complex in general. Right? This is cosine theta plus I sine theta, right? Cosine e raised to I theta, remember, is cosine of angle theta plus I times sine theta. So in general, these are complex numbers. So if these are complex numbers and this is real, it's expected that the coefficients of these functions are going to be complex in general. So electric field is real in the position and time space, but it doesn't have to be real in the frequency and the wavelength space. In fact, Refractive index, is it real or imaginary? The refractive index that we always study in elementary physics. What is refractive index, by the way? Anyone? How do you define refractive index?
It's the ratio of the speed of light in a vacuum to the speed of light in that material.
Perfect, right? So refractive index is the ratio of the speed of light. So let me write this here. So erase this. So refractive index, N usually we call it. So it's speed of light in vacuum over speed of light in medium. Speed of light in medium. Can this be imaginary? Okay. In this way of defining it doesn't seem like at all, right? Velocities has to be real. But we already saw that speed of light is epsilon naught times mu naught. Right? So that's your speed of light. So this gets upgraded. So this we will see. We haven't shown yet. This will become epsilon over epsilon naught and mu over mu naught. So that's how your speed of C is this. This is in the medium, and this is always greater than 1. And this quantity.
That equation there should not be 1 over the square root thing.
Yes, yeah, that's what I was thinking. Thank you. The inverse or 1 over C. Thank you. Okay. So it can be complex, and that is the same features we are talking about here. That's because we are in the Fourier space. If anything related to color, we are in Fourier space. Fourier space quantities can be imaginary. So refractive index can be complex. In fact, whatever we usually say in the lab that refractive index is 1.5 for a glass, right? That's typically the number is 1.5 or 1.6. That's a real part of the refractive index. As an imaginary part of the refractive index also, what would that mean? Any thoughts? Ever seen that? The real part is typically the actual refractive index that we see in optics in undergraduate physics. Yes.
Is it the relationship of frequency that it becomes imaginary?
No.
Okay.
There might be something like that. Maybe you have something in mind, maybe, but I'm asking much more broader point. The imaginary part of the refractive index is a measure of how much light will be lost in the medium, like dissipation of the medium. And the beautiful part in all this is, again, we will see how much we can go. I'm here just digressing to the topic. Some of you guys are taking math methods. There you see what is an analytic function, right? Analytic functions are very special functions which are constrained in such a way that if you know its value in some part of the region of space, you know it everywhere. And refractive index turns out to be, to our best of our knowledge, if you know the real part, you know the imaginary part already. So these are not independent quantities. Like if you know how much is the refractive index, how much it's going to reflect, the material already knows how much it's going to absorb. Which in the physics sense, it's not very surprising. If you think of reflection, how much comes in, how much is reflected is also related to how much you transmit if you think of conservation of energy. So that's the idea that comes in. And it turns out that this is an analytic function, actual analyticity in math methods shows up in. So those are broadly speaking how the Fourier transform plays a very big role in this whole system. But for us, it's just going to be a mathematical tool here in this manner. But again, as I said, frequency is physical. So you need to pay attention onto that. And the inverse, the inverse Fourier transformation is d cube r t. This is supposed to go from all space here in the k space minus infinity to plus infinity, all three integrals. And this is minus a cube dot r minus I omega d or plus I omega d times e of t. And we also said that this could be partial, even as I already pointed out, sometimes it is only the frequency that is important, and we will do only the time will be Fourier transformed position. We will keep it as it is, that will already used as we proceed. So if that is the case, then it's a good thing to ask, at least in this simple scenario where all the coordinate, all the position, and all the time is Fourier transformed. How does Maxwell equation look like, right? That's the first thing we can try. So let me go through slowly in this, just to show you the steps that comes in. This was also a partial, what is this, extra credit problem. So some of you guys attempted, so it must be familiar, hopefully, but if you're not got the steps, just look into this. So let's start with del started with G is equal to a row of RT. This is R and T. And substitute your Fourier. And this, I should also point out that I wrote the Fourier transform in terms of the electric field, but this means that any field can be transformed like this. It could be D, it could be the magnetic field, it could be the current, the charge density, it could be the current density, anything, and even a scalar. If it's a scalar, this is just becomes a scalar, this becomes a scalar. I wrote it for a vector, but this is a general function in general. Okay. So that's what it is, dotted with d cube k over 2 pi. E raised to pi. And the same thing here. D cube k. And since there is not much space, I'll write the exponential here. It's the same exponential that shows up here. I'm just trying to save space there. And this is a row of k omega. Hopefully that's not confusion. Now, usually the trick in at least Fourier transform as such is a big field in mathematics, but in physics we are mostly using it as an application. Like we are at a user level, if you want. You're not actually looking at the properties significantly. So this is a practical part of Fourier transform. How an important step in the Fourier transform mathematics. Notice that the time dependence here was R and T. The only time dependence, all the time dependence, if you want, has been captured inside the exponential, and everything else, these are all not having time dependence or time or position dependence. Right? That's the idea of Fourier transform, that you expand it in terms of eigenfunctions, and then there are coefficients, which are known eigenfunctions. We know what the eigenfunctions are, the properties. So these are sine and cosines, for example. But the price you pay is that you're inside an integral. So you can go to the Fourier space, you know how to work with it because it is exponential, but you have to get out of it. But getting out of that involves an integral, which is usually not trivial at all. Integrals are not easy. So most of the time you're stuck there, you cannot come out. So there are very simple, very few problems in which you can go and work in the Fourier transform and then come out also. But we have developed a lot of techniques. So that's one of the major techniques that we use, that you go into the Fourier transform, work, and then come. Okay, so that's good. So that's so this gradient here then only sees this. So I first bring this gradient inside. It sees only the exponential, and we know what it does on an exponential. This is so it looks only at the eigenfunction. And what is that equal to? It brings down an ik, right? It acts on this r. Whatever is in front, it comes down, but since it's a vector, it is basically ik vector times the same exponential. But this is inside the integral now. Clear? Right, you bring this gradient inside because these are not position dependent integrals. I can bring this inside. When I bring it inside, it hits only on this exponential. It doesn't hit on this. But then I know how to work on that. And then I get a k. But now I cannot go out because this k is an inside of the integral. I cannot bring that k out. So you're stuck with that integral. That's the price. Before I write that down, there is one more thing I could have done. There could be a time derivative sometimes, right? There could be time derivative. I k dotted with r minus I omega t. And because of this negative sign, there is a minus I omega exponential I k r. Right? All the gradients become I k, and all the time derivatives become frequency, if you want, imaginary frequency. So your equation becomes e cubed k over q pi cube omega over 2 pi and that's I k. Since I left that, so I can keep using that. That may be lazy a little. So exponential k omega is equal q exponential, but this remains the same, right? Rho k. Notice both have this exponentials common. Let me rewrite this equation as cube k over 2 pi cube exponential you have IK times the electric field. Oh, what is missing in here? Something is missing, right? Some small details in here. There's a dot product between these two vectors. Right? So this was a dot product between gradient and the electric field. There has to be a dot product between K and the electric field. There's a dot product, otherwise this vector nature doesn't complete itself. So this is, and it shows up here the moment you move that electric field. That's K dotted with E. And this is in the Fourier space now, K omega. And when I move this to the left, so it's minus rho in the Fourier space, which is K omega. And again, I've said this before, that in principle, this should be a different function. Right? In a Fourier transform, this should be tilde, for example, or primed function. But I'm using the fact that if the variables are different, I'm implying that that's a different function altogether. So there's a dumminess in the notation here, or ambiguity in the notation here, but the that's being filled in words. Okay. Any questions on this step? As of now, this should be very clear because very soon, as we proceed, we will start from here and immediately, not even this, we'll write down the next step. So we will, whenever we'll see a gradient, we will pretty much replace it with IK. That's what it will be. But there's more than just gradient changing to K. Notice, as I said, this is inside an integral, right? The price we are paid is that we are now inside an integral, and if you want to get any results in position and time, I have to do this integral, complete this integral, which is usually not easy. But even more than that, these are complete functions. Fourier eigenfunctions are complete functions. What that means is that if I can write any function in this form, and if its coefficients come out to be 0, that means the coefficients themselves are 0. So let me elaborate on that. Exponential of I omega t, right? Whatever we are saying is Fourier eigenfunction. That's like unit vectors in a vector space. So that's like I hat, j hat, and k hat. Right? Just that these are infinite of them. For every omega, there is an eigenfunction. Here there are only 3 of them. Right? So there is a one-to-one correspondence between a vector. So this is called a vector space in many ways. Fourier space is a vector space, and in another context, probably in a mathematics course, you will see that in more elaborate form. But these are unit vectors. That's why they're called basis vectors, right? Actually, if you've done math methods with me, we talked about basis vectors. So these are actually basis vectors. We call it eigenfunctions in this scenario. They're nothing but basis vectors that we discussed there. When they're finite dimensional spaces, you call it basis vectors. If they become infinite dimensional spaces, that means to say there are infinite eigenvectors or basis vectors you call them eigenfunctions. Okay, so but the concept remains the same. The challenges come out to be that if you have infinite of them, the convergence might be an issue. So those are the challenges come in, but we always work with nice, well-defined spaces. In that sense, these are components now. These are components now, right? This is a vector in a vector space. Already this is a vector, but even the position dependence is a vector in an infinite dimensional space, and these are its component. And if you have a vector, right, so a1 I hat plus a2 j hat plus a3 k hat to be equal to 0, what can you say about a1, a2, and a3?
Could you move the board or move the camera a little high, I guess?
Better?
Yeah, we can see that.
Okay. If you have a vector which is equal to 0, what can you say about its components? It's also 0, right? The moment you have a vector which is 0, its components are 0. That means to say that if I say the electric field is equal to 0, right, everywhere in space and time, it immediately means that its components are 0. All its components are 0. For every frequency, for every wavelength, they're 0. Right? If this is equal to 0, because it's a complete space, notice your vector, right? And it's not always true that if something is 0, something else should be 0. This is a product in the sense a1 times I hat. Because it is orthogonal space, then it implies that a1 is equal to 0, a2 is equal to 0, a3 is equal to 0. In that sense, now if you were to interpret this equation, this is these are eigenfunctions. Whatever these are components of something. Right? This is actually a field here, right? But that's equal to 0. If that is 0, that means every component of this is 0. It's not immediate that it should always be the case. But if this equation comes, and this is because it is a complete set of functions, it is like I and j and k. If you can expand something in terms of I, ij, and k belongs to a vector space. So similarly, you are expanding some quantity in terms of this, and this, after you subtract this out, that's the components. If that is equal to 0, whatever is in the square brackets is 0. So this implies, right, a lot of concepts that went in from there to here, that ik dotted with e. Now in the Fourier space, right, is minus 0 k omega is equal to 0. So you can say so that's your first Maxwell's equation in the Fourier space. The way to interpret is that at least at a maybe a very remote connection here is that when you think of a projectile motion, right, when you throw a ball and it goes to a certain extent, typically what you do is you break it into x component, y component. X component obeys kinematic equations separately. Y component obeys kinematics equations separately, right? You do both the calculations separately, you reach at the final point, and you combine them together. So here what we are saying is that this is the Maxwell's equation. This is the equation that each component of the electric field will satisfy. Electric field has a lots of components for each frequency, and for each wavelength, it has components exactly like the x and y components of the projectile motion. But each of them satisfy this equation separately. So in the very first instance of time, you can split them up and evolve them separately and then bring them back to you. So it's kind of, they obey linear superposition principle. That's what that's a linear linearly adding, right? And in projectile motion, what is the connection between the two x and y components? It's a time. Time that connects them. Time is common in the two cases, and in this case also it is going to be time, but here it gets more messy because time itself is Fourier transform. So that will be the complications in there, but in very simple terms, this is what we are doing. We're splitting our function into many frequency or color if you want. That's usually more intuitive because we are used to optics and color, like white light going into red, blue, and green. So we are thinking of any light to be made up of any frequency. We'll split that into Fourier components and work with Fourier components. So that's your first Maxwell's equation in the Fourier space, in complete Fourier space. That means to say both frequency and wavelength. Sometimes you do it only in frequency, then only you do the time case. That's also perfectly fine. Okay. So hopefully that gives a feel for it, and you'll start using this more and more, so you get a lot of experience. This is for one equation. If you do it for all the equations, you get. So this is ik dotted with e. So if I leave it as e alone, then it's a little ambiguous, right? Am I talking in terms of position or frequency? So in these cases, it becomes necessary to write the dependence. This is correct. If I were to do it this partially, this is also correct. So R omega, because there is no time dependence in here at all, this is also true. But this electric field is very different from this electric field. Right? This is only in the time domain I have Fourier transform. Here I have Fourier transform both time and position. If I Fourier transform both time and position, gradient also lifts to k. Here I did not do anything to the gradient, right? In fact, I did not do anything here because there was no derivative time dependence at all in this equation much. So that's one thing. If I do the next one, it's very clear what I'm doing. Just replace the gradient with I times k. That's equal to 0. And here this is So next equation is the Faraday's law. It's not probably one might be wondering, or does the cross product go through? We only did this for dot product, but we saw that the dot product was pretty much going through the integrals in and out very smoothly. So instead of dot, cross also goes through smoothly. So if you're worried, just go through the steps again, repeat it, and you'll see that it goes through. There is a time derivative here now with a negative sign, but time derivative goes with minus I omega, so this becomes I omega times the magnetic field. Notice it changes sign. If I were working in a partial Fourier transform, then this will be gradient stays the same. And this will switch. Okay. Is that clear? Any questions? What I'm doing here? This term becomes minus I omega G. This will become that's good enough. That was simple. Once we learned one trick, we just went through the whole. Correct. Any questions there? And your homework involves this. So it basically involves this, not even that. Your homework is you begin from here and you process this equation. Notice that is a significant. Why do we like to go to Fourier transform? It's a common feature if you're doing any kind of analytic derivations. It becomes very convenient to go to either Fourier transform or any kind of space. You might have Fourier transform is the easiest space you can think of. Whenever you have linear symmetry or the way is planar symmetry, you do Fourier transformations. If there is spherical symmetry, that is a more complicated or more useful version, you can say, inside, and that's called harmonic. What is it called? Spherical harmonic. So there are different functions. You might have heard of different function spaces, Bessel functions, Hermite functions. If you've done complex quantum mechanics, if you remember your undergraduate quantum mechanics, harmonic oscillators, how do you write your solutions for harmonic oscillators? They're called Hermite functions, like these are called special functions in general in math methods, so special functions. Some of them are very common. Let's see. Hermite functions. Then you have Laguerre functions. You have Legendre polynomials. Functions that they are called polynomials. Then there is spherical harmonics. And what else? Bessel functions. And yeah, let me stick to this. I think these are the ones you will come across in one of your physics subjects in the next 3 semesters. So since we have an extra credit, this is useful. I think this is gives you an overall perspective of where this is. In math methods, you look at this as different functions. But these are all usually used whenever you have a symmetry in a system. Okay, I should also write Fourier, right? Fourier was the first. Fourier. So try to get what symmetry in the problem motivates you to use one of this. So as a hint, I would say that this is planar. It is not strict that you have to use it for that purposes, but that's what it is mostly used for. You can use Fourier space anywhere. Any function can be Fourier expanded. Any function can be expanded in terms of spherical harmonic, but you often use it in specific scenarios. So whenever you have planar symmetry, a lot of planar symmetry, then you use Fourier. Whenever you have a lot of spherical symmetry, you use spherical harmonics, and this is also for spherical. I mean, you should try to understand what do I mean by two. This is the radial functions, and these are angular functions. And try to understand where this shows up. And if you want to get more insight into this, each of these are related to differential equations. Differential equations. That's what broadly, that's what we do in physics. We try to understand some systems and you try to get some solutions out of it. And based on those solutions, you can extend further. Non-trivial solutions are also possible. But try to make a chart in your, you should be able to find this with a little search that in what symmetries does this work and what is the differential equation associated with this. This should be a good exercise for you to get a bird's eye view of what's going on. But all of this, whatever said, these are differential equations. Differential equations are hard to solve. What we have done by doing this is that this has become algebraic. This is K. This is not a differential equation anymore. Right? So by going into the Fourier space, what I've gained is that I'm not solving differential equations anymore. These are algebraic. I can solve for E. This is A dotted, two vectors dotted is equal to something else. It's easier to solve than you're solving a differential equation. To solve for the electric field, for example, what we're saying is that if it was one dimension, K times E is equal to rho, right? If it was one dimension. So E is equal to rho over K. Compare this with the other possibility that this is how the differential equation would have looked like. This is a little more work. Right? I will integrate this to get the electric field. Right? So this is just, it has become algebra. But the price I have to pay is that I have to go back, like I have to do an integral. It is the same amount of work as this. I have not gained anything, but yes, yeah, whatever you mean by that. Yes, you gained in the sense that we know how to operate with Fourier transforms. And then you even do something that there are lots of components, like think of music. Yeah, so here is how does YouTube work? Have you guys heard of this? Like 20 years back when YouTube was there, so one of the challenges that comes about is, if you notice, a size, okay. A movie involves a lot of data, right? There's a lot of information that you have to go from here to there. Right? And if you try to do a simple estimate, and if a movie has gigabytes of data, lots of data, let's say, and you want to pass on each and every information onto the other side live, right? Exactly now whatever is happening in Zoom, there's a lot of pixels here we are constructing, and we are actually passing that on in live. Like at every instant, we are possibly transmitting a lot of information. And that was considered, like if you're 20 years back, if you had asked the same problem and the internet was just beginning, you would have said, oh, that will take ages to do this. But we are almost using the same processing power. But what we are doing is the following. If you're doing music, we know that our ears hear only 20,000 to 20,000, sorry, 20 to 20,000 hertz. Right? So our frequency is only 20 hertz to 20,000 hertz, 20K hertz. So if you think of this as a Fourier transform, there are lots of components here. I think of music as tones, right? There's a lot of tones. But when you actually Fourier transform, there will be a lot of information on the left side of 20 and on the right side of 20. But what YouTube came up with this, or YouTube or all this fast Fourier transform, whatever the technology they came up with, is that you don't want this information. So delete that right away. And in fact, they don't even stick to this. Like they learned very quickly that we don't have to transmit this much information at every instant. For example, do the differences. That's one of the tricks you can use. Like if I'm passing on an image, I don't have to transmit my image at every instant. Look for what are the differences from one instant to the next instant. Most of this whiteboard remains the same. It's only my eyes that are blinking most of the time. My hands are changing. So most of the image stays the same. It's the differences that is transmitted. Or that is, those are tricks, but the biggest idea was to do the Fourier transform and pass on the Fourier components to that. Don't worry about the function itself. Let's work in Fourier transform. And that is one of the big deal that at least 15 years back when first time YouTube came in, that was, it actually excelled in that idea. And then everyone started using it, and these days movies are very easy. So look it up. I think there are, I haven't actually looked into it any one of them seriously, but I do see sometimes when you click on this YouTube channel, there are good videos made of how YouTube is able to pass on so much information, like a whole movie within a small amount of file. So look it up. There are nice videos as far as I know. Okay, so but now we need to do one more thing, and that is in the last 7 minutes I have. We also constructed continuity equations, right? So, for example, let's write the energy continuity equation. That's the U, right? This is R of E now, plus convergence of S of RT plus what is it? This was rho J dotted with E. I want to write that as of P. Let me think of it as P. I mean power there, because these are all dimensions of power density, right? Small p, capital P will be power, small p, power density. And this equation immediately, I know how to switch over to a Fourier transform. The same idea, right? Switch over to Fourier transform. This is minus I omega U of, let's switch to both K and omega. So this is plus IK dotted with S of K omega plus P. Okay. Now here is where there's a small caveat here. One should be very careful. In this way of writing and our notations, it seems like U and this U and this U are Fourier transform of each other. But they're not, because these are bilinear. So U of RT is equal to, what was it? Let's do S actually, because that's less number of terms. I'll only mention this whenever we come across this, we will again use this, bring it up. S is E of RT crossed with H of RT. Right? And S of K omega is not Fourier transform. So let me just, it's not Fourier transform of S of RT, because they are bilinear. bilinear means there have two pieces in it, right? There's double construction in it. So that leads to a small extra credit maybe. Again, we'll do this whenever we come across these things later. In future, we'll be using this again. And I'm just warning you at this stage is that this, when you have, what is the Fourier transform of f times g? So f goes to f tilde, right? That's your Fourier transform. What is the product of two functions? How does the product of two functions Fourier transform? And think of convolution. Like if you have studied Fourier transform in any math course before, you should look up convolution. So they get, the idea is that they get completely convoluted in the frequency space. Just look it up. So the only thing I want to warn you is that there is a one-to-one correspondence here, but these are bilinear constructions, so the interpretations change a little bit. And whenever we reach that, we will start using them again. So we'll have a lot of opportunity to clarify this. At this point, I'll stop here, and from the next class onwards, we'll do Maxwell's equations in macroscopic domain. And one of the things we will do is Kramer's chronic relation, which is significantly important and takes a lot of confusion associated with it. So we try to do that in maybe 2-3 lectures. It basically deals with causality. How does causality look like in the Fourier space? That's the main idea. Thank you. Any questions, comments? You will.
What did you call the thing you just said?
Kramer's chronic relation. So this is causality. Relation is, it's a very, I would say, look it up. Kramer's chronic relation. I also pointed out that refractive index and absorption, how they are related, that they are related by Kramer's chronic relation. If you know the refractive index, you know the absorption. In fact, that is how exactly it is done in a lab. The lab will measure one of the quantities, usually it is the refractive index, and then the absorption is, they use the mathematical relation. So theory is used to predict the absorption. That has become so standard these days that because measurements are not so accurate, so we will depend on Kramer's chronic relation. But very mathematically very deep concept. It depends on the properties of an analytic function in complex variables. So, pretty nice. So try to understand that it is kind of nice. You might have also in popular level heard that slowing down of light, like there are labs which, so basically if you go into a material, because of refractive index, velocity slows down, right? And how they achieve that, and often there is a lot of misclaims, if that's the right word, right? Saying that, oh, we can go faster than light. So lots of wrong conclusions can be made if you're not very careful about causality. And causality is not at all trivial when you go into the analytic or the complex frequency space. Not at all trivial. Actually, that's the statement. Kramer's chronic relation is the statement of causality in the complex, in the frequency domain. Very non-trivial, and that leads to a lot of confusions if you want. But most of the people understand it then. So for example, if you've heard of metamaterials, metamaterials are materials in which, these are popular, like kind of cool things, but very hard. Like if you have light coming in, this is familiar, right? That's how light behaves if you go from a rare medium to a rare to denser. So there are materials where very popularly you would say that the light comes from here and it goes this way. Okay, so these are called metamaterials. And they're mostly, in the beginning, there was a lot a lot of confusion about this, that was not accepted, but these days it is accepted in the last decade. Topological insulators have this property. Like topological insulator that got Nobel Prize recently in the last few years. That has this, some of us do this in our labs here in our department, so some of you probably will be using it. That has this property, very counterintuitive, stems from, it begins from this Kramer's comment. We won't be able to do that much, but I might be able to give hints. Mostly I don't cover them because I'm myself not so confident at it. I like those topics very much, but one has to be very careful when you're actually teaching. You don't want to do the wrong thing. So I'll encourage you guys to look it up, and the content will be there, but some of interesting. Yeah. So look it up. That's all. That's the best way. Okay. Thank you.
Thank you.
You.
Oh, Khalid showed up.
Yeah, he's been there.
He's been there. Oh, you saw that from the very beginning? Oh, I see.
Pretty much.
Yeah, I didn't notice. Okay, guys. Bye.
It was just his name.
Yeah.
Bye.